అలాగే సార్. నేను పంపించాను ప్రభాకర్ రెడ్డి గారికి మాట్లాడండి. అలాగే.
Hey, hi, good evening, everyone. Good evening, team. Good evening, friends. Right. So, welcome back to our
సార్.
module 2, the ongoing series. Welcome back to our YouTube channel. So, it's been our second day. Yesterday, we got introduced to the topic linear regression. There are a few more topics that we are supposed to do it. Okay. Anyhow, we are going to understand as part of these sessions. So we'll quickly recap what we have covered in the previous session. Then immediately we'll learn. Right. So right. So in the last session, we understood what is regression. 1 minute. We understood what exactly is regression. What do you mean by regression, friends? No. Regression means the algorithms that they work on continuous data. Okay, even in the morning session, in the forenoon session, we have discussed the differences between classification and regression. Okay, for discrete data, we go and use classification algorithms. For continuous data, we use regression algorithms. Out of all the regression algorithms, very widely used algorithm is linear regression. Linear regression is widely used. Yes. So when you talk about regression, again we have multiple algorithms that are available under regression. We have linear regression, logistic regression, multinomial regression, then ordinal regression. Depending on the use case, we go and use. Okay, so the regression type. Yes. Linear regression is generally used when the values under the y column are continuous. Okay, then what about logistic regression? The next topic as part of this particular playlist. Okay, so under logistic regression, generally this logistic regression is used for you know binary classification. If the values under the y column are of two classes, only binary, then we go and use logistic regression. Right? Anyways, this particular topic we'll learn in the next 2 3 days. But let us continue with linear regression. So yesterday, if you remember, we understood this using linear regression. We are going to establish a linear relationship between our input and outputs. Okay, so the same equation of straight line will be considered, and using equation of straight line, we are going to achieve the y is equals to f of x equation. Okay, so we are going to form a straight line as part of linear regression. Okay, a linear line is going to be created, and this has to be the best line. Okay, if you observe the plot, if you observe the graph, there is scatter. Okay, we have considered the inputs on the x-axis and the output on the y-axis. Okay, so we have the scatter, and we are supposed to get the best fit line. So how can we achieve the best fit line? What technique is used, friends? OLS technique is used. Ordinary least squares technique is used. So the main objective of ordinary least squares is to reduce the error. What is error? What is the formula for error? Respond here. What is the formula for error? Actual minus predicted will be our error. Actual minus predicted will be our error. Okay. So this particular minimizing the error will be the objective of OLS, ordinary least squares, and that can be achieved when you keep on iterating. Okay, when you see the equation of a linear regression, it will be like this: y is equals to beta naught plus beta 1 x1 plus beta 2 x2 plus beta 3 x3, so on. This is the equation of a linear regression, right? Where beta naught, beta 1, beta 2, beta 3, so on are coefficients. X1, x2, x3, x4 are, what are they? Inputs. Okay. Y is nothing but r. Okay. So initially what happens is these with some random values, and when you pass inputs to that equation, you'll get predicted value, nothing but y cap. Since you already have y minus y cap will be, am I right? Yes. So this error should be very small. Minimizing the error is the objective of OLS. OLS works with an objective to minimize this error. So how this error gets minimized is, there is a kind of terminology called back propagation, but that is not the right terminology that should be used here. So what happens is these coefficients will get updated. Once after these weights get updated, what happens? Your predicted value will be very close to your actual value. So when both of them are all, the error will be very small. Yes. So this is how linear regression works. And what are the important assumptions that we have discussed yesterday? Linear regression works on line assumptions. What are the line assumptions that we have? Come on, friends. What are the line assumptions? Line assumptions represent linearity, independent, normality, equal variance. Okay, so when you observe what should be linear, the first one talks about linearity, right? Both dependent and independent variables should be linear. Okay, the relation should be linear. And what should be independent? The observation should be independent of each other. The records that you have should be independent of each other. Then, when it comes to normality, the errors that we get as part of our training, the residues of the model should be normally distributed. Okay, the errors, when you take the errors and when you try to understand distribution, equal variance, which talks about homoscedasticity. Okay, so constant variance should be observed with respect to the errors. Okay, how do you define an error? Error is nothing but actual minus predicted. Okay, for all these errors, we should observe a constant variance. The variance should be constant across all the errors with respect to the training process. What if the variance is not constant across the errors? That is called as heteroscedasticity. Okay, so that is the difference. And friends, you're supposed to remember the terminology: homoscedasticity, heteroscedasticity. Then we should not have any kind of multicollinearity issue. What is multicollinearity? What exactly is this problem? Multicollinearity talks about the independent variables if they are correlated. Okay, if x1 and x2, if they have a correlation, if they are related to each other, okay, then you can say we have multicollinearity issue. This should not be present. That is the assumption, right? The assumption says no multicollinearity. All the input features, all the independent variables should be, they should not be like correlated. If they are correlated, that means we face multicollinearity issue and we are supposed to overcome it. Okay, then no autocorrelation. So this autocorrelation talks about the residues, the errors. Even the errors should not be correlated with each other. If they are correlated, we say the errors are correlated and we have autocorrelation issue. So line assumptions are important. Along with the line assumptions, we have three issues. One is heteroscedasticity, then multicollinearity, then auto correlation. Okay, so focus friends. These are the issues and these are the assumptions. If we have any of these issues, we are going to overcome them. We'll apply some kind of solutions to overcome these issues. Right. Then the types. What do you mean by simple linear regression? I want everyone to answer. What do you mean by simple linear regression? Linear regression is of two types. Tell me the two types first of all. The first one is simple. Good. The second one is multiple. Simple linear regression, multiple linear regression. On what factor did we, divide linear regression into two types? Based on inputs. If we have only one input, okay, then we say, one input, one output. Then we say it as simple linear regression. Then we use simple linear regression because the equation will be like this: y is equals to mx plus c. Simple. Only one input, one output. Okay. What about multiple linear regression? If you have more than one inputs, it might be 2, 3, 4, so on, and one output. It is nothing but multiple linear regression. Okay, so based on inputs, we have divided linear regression into two types: simple, multiple. If you have only one input, go and use simple linear regression. If you have multiple inputs, go and use multiple linear regression. But the concept is same. Only the number of inputs changes. Okay, when the number of inputs changes, ensure that these inputs are not correlated. If they are correlated, you have an issue that is called as multicollinearity. But can you get multicollinearity in simple linear regression? No. Why, Akhil? Why can't we observe multicollinearity in simple linear regression? How? You have only one input, right? So I hope it's clear. So we also discussed the example by taking one feature. Then, so this is the example for multiple linear regression where we have more than one. Am I right? Yes. This is the equation for multiple linear regression. Good. And we also discussed how OLS works. It works on the objective to minimize the error, actual minus predicted, where all the discussed. Okay, and we discussed the differences between homoscedasticity and heteroscedasticity. Simple, in short, how can you observe whether you have homoscedasticity or heteroscedasticity is a scatter. Okay, whatever the scatter that you see, one minute, yes, the scatter that you see, if it's between two parallel lines, you can say it as homoscedasticity, and if it is uh, spread across a kind of non-parallel lines. These are parallel to the regression line, to the best fit line. But are they parallel? No. So here you can see it is heteroscedasticity issue is observed. Okay. And we also discussed correlation coefficient. Correlation coefficient, what is the use of small r, friends? Why should we use small r? Friends, did you get my question? Why should we use small r? What is the use of going and calculating small r? It finds the relation between two variables. Simple. Small r gives the relationship between, how is the relation between two variables? The range of small r is -1 to +1. Okay, and if you take only the magnitude of r, it is 0 to 1. Based on this range, you know, the strength has been segregated. If R greater than 0.85, we say the strength is strong. If R less than zero point 0.4, we say the strength is weak. And if R lies between this range, we say strength is moderate. And what about the sign? Sign talks about the direction, friends, either upward or downward.